about 20 feet that way. Petting cute little animals is probably more interesting than going to this class, but arguably learning optimization is more useful. So today we're going to talk about duality. We're going to finish off our duality lecture from last Thursday, and then we're going to move into Kkt conditions. So just to remind you of what we kind of covered last time up until this point, we learned about this thing called the Lagrangian, and from that we can form the Lagrange dual function. So here was our setup. We had this generic optimization problem. Minimize this function f of x subject to these constraint functions hi of x less than or equal to 0 and lj of x equal to 0. And we're not going to assume it's convex, but of course we'll pay kind of special attention to that case. So the Lagrangian is just formed by taking f and adding multiple, or a real number times each constraint function. And where these real numbers we call dual variables. So we introduce these variables ui and vj, one for every inequality constraint and equality constraint. And we restrict the ui's to be non-negative in every coordinate. And so this is how Lagrangian is defined, just by taking f of x and adding on the sum of ui hi and the sum of vj lj. So it's a function of three variables, now x, u, and v. X is our original variable. We call it the primal variable. And u and v, we introduce these variables. They're called the dual variables. Okay, and implicitly, this Lagrangian has a domain where it restricts that u to be non-negative in every component. So we can think about it like it's minus infinity if we ever pass it a u that has a negative component. So there's this important property, which is that if we take any u that's non-negative, and any v, and any feasible x for our optimization problem, the Lagrangian forms a lower bound on our criterion value at x. That's seen just because each hi at x is less than or equal to 0 because x was feasible. So when I multiply ui times hi, this component is less than or equal to 0. Right here you can see it's important that ui be non-negative. So this whole term is going to be smaller than or equal to 0. And this whole term is going to be equal to 0 because each lj was equal to 0, just by feasibility again. So this is less than or equal to f of x. Okay, so here's a picture of that where I had, this was my function f of x, this solid function here that's drawn as a solid black line. And then in dotted lines here, I'm drawing the Lagrangian. So here there was just one constraint on this function, and that it's that it has to be within this interval. So actually I have two inequality constraints here. Okay, so I introduce two Lagrange multiplier parameters, right? One for each of those inequality constraints. And here is the Lagrangian as a function of x for various values of those dual parameters. You can see that it lower bounds the function within the feasible region. Okay, so each one of these dotted curves is like L as a function of x for some fixed values of u. There's no v here because there's no equality constraints. Okay, outside of the feasible region, it does not lower bound our function. That's obvious because then hi will be not necessarily less than or equal to 0, so we won't get that this is less than or equal to f of x. The Lagrange dual function is just defined by minimizing that Lagrangian over all x, unconstrained. So not over x within the feasible region, just over all x. Right? So this very simple sequence of arguments tells us that the Lagrange dual function provides a lower bound for the optimal criterion value on our function. This is very simple stuff, but it's fairly powerful what we get out of this. These arguments look very kind of simple and maybe a bit subtle. But so f of x, right, f star is the minimum over all x that are feasible. We'll call that set C of f of x. Right, and because f of x is lower bounded by Lxuv for all x, that's going to be bigger than or equal to the minimum over all x and c of Lxuv. And if I remove the constraint set here, if I just take the minimum over all of Rn, then I'll get something even smaller. And this is how we define the Lagrange dual function. So that's GUV. It's the minimum over all x of Lx uv. Okay, so f was a function of x. Our dual criterion G is now a function of u and v. Okay, so here was this same example. I'm just plotting the dual function as a function of one of its parameters here. It's called just drawn as lambda in the plot, and you can see that it's always less than or equal to this dotted line, which is f star. It was the optimal value of our primal criterion for that same last example. Okay, so we derived the dual function for a QP. It turns out it was also a quadratic. So if the primal problem is to minimize a quadratic subject to equality, linear equality constraints and linear inequality constraints, it turns out that the dual function is also a quadratic. So we derived that in closed form right here last time. And this was just a slightly more general case. And we had this example that showed us that if I look at the primal function and the dual function, it looks like that the minimum value of the primal function and the maximum value of the dual function, which is also a quadratic, happen to agree. Okay, so we're going to talk about when that's the case in the rest of these duality slides in general. So we have this constructed lower bound, right? This is true for any u that's bigger than or equal to 0 and for any v. And now to get the tightest lower bound possible on the optimal value of our criterion for the primal, we'll maximize this function over all such u and v. Right? That makes sense because this holds for all such u and v, so the maximizing this function over u and v is going to give us the best lower bound. So that's just the Lagrange, that's called the Lagrange dual problem. So we have minimize f of x subject to, I'll just condense the constraints as x and c. That's the primal. We know that this value is lower bounded by GUV. So we'll just maximize overall u that's bigger than or equal to 0 and all v GUV, and we'll call this the dual problem. Okay, so the optimal value here is f star. The optimal value here is g star. We'll call it g star. Because it's true that for any uv, GUV is less than or equal to f star, right? That's what we had up here. It's certainly going to be true that f star is bigger than or equal to g star, right? Because this was true pointwise for all uv, so it's certainly going to be true of the maximum. So this is called weak duality. It means that if I look at my primal problem and I solve it, and I'm able to form the dual problem and I solve it also, I know that the two optimal values of the criterions have to obey this relationship, that f star is bigger than or equal to g star. Okay? Nod your heads if you guys followed this, if this makes sense. Okay, good. So this always holds. It's even true if the problems are non-convex. I didn't actually use anything to do with convexity for these sequence of arguments. We never relied on convexity. We just said if we have a primal problem and we're able to derive its dual problem, then they obey this relationship. So we always can get a lower bound from the dual problem. This is kind of interesting, and there are some applications of duality, of weak duality, where we only really need to use the less than or equal to formulation. But what's really interesting is going to be this. Is one of these two equal? Because when they're equal, we're going to see that actually there are cases in which we can get primal solutions from dual solutions and vice versa. So where we can actually, instead of, say, solving the primal, we can solve the dual if it's easier, or vice versa. And for that to happen, we need to know that these two optimal criterion values are equal. that's really the more interesting question with duality. So we'll get to that in just a few slides. Okay, another key property besides weak duality, which always holds, is that I claim that this function g here, gu v, is always concave. And I claim that's true regardless of whether f was convex or not. Which means that if I have a non-convex optimization problem and I derive its dual is always a concave maximization problem. Right? A concave maximization problem is equivalent to a convex minimization problem. Right? Because I can write maximize GUV as the same thing as minimize minus GUV. Right? And if G was concave, then minus G will be convex. So this guy is a convex optimization problem. That's true no matter if f was convex or not. Okay, so again, the argument for that is very simple, but you can see how powerful the implication is. Right? The implication is that the dual problem is always convex, always a convex optimization problem. So why is that true? Well, we can just look at what I have written on the slides. The dual function, by definition, is the minimum of the Lagrangian over all x. The Lagrangian was f of x plus the sum of ui hi plus the sum of vj lj. And I'm going to write that. So I'll write min over all x of the Lagrangian xuv as minus the maximum over all x of minus the Lagrangian. I haven't changed anything by doing that, right? And I'll just fill in for the Lagrangian. This is f of x for minus the Lagrangian minus the sum of ui hi of x minus the sum of vj times lj of x. Each one of these functions here for a fixed x, right? So each one of these functions for a fixed x is a convex function in u and v. Why is that true? What kind of function is that in terms of u and v for fixed x? It's just a linear function, right? Or it's an affine function. So trivially, this is a convex function in x. And what am I doing? I'm taking a maximum of a pointwise maximum of convex functions. Right, so this pointwise maximum now as a function of u and v is going to be convex. Then I take the negative of that, and it's concave. So I've just said, right, that GUV, which is equal to the minimum of the Lagrangian over all x, is something that's minus a pointwise maximum of convex functions. So it's concave. So does this mean that I can always take any non-convex problem and solve its dual? Does this slide tell us that we can always just take a hard non-convex problem and solve its dual problem? What's the catch here? There's kind of two catches. You're shaking your head. This part here. So in other words, right. So another way of saying that is that it could be very hard just to derive the form of G. It could be the case that even though we know that G is a concave function and it's defined by this equation, it could be hard to actually write down an analytical expression for G. And in fact, that will be true generically for non-convex problems especially. even if we could, for a non-convex problem, derive its dual function in closed form, if we had an expression for GUV, at this point, we still only know that by solving the dual problem, we get a lower bound on the optimal criterion value. Right? So again, there are cases in which that's useful. There are times in which having a lower bound on the minimum value of the problem is really very useful. But this doesn't kind of in any way equate non-convex problems with convex problems. But it's still a nice relationship. So here's an example that I wanted to just go through quickly that uses the fact that the dual function is always concave. So I took this function here, f of x, which is x to the fourth minus 50x squared plus 100x. It's non-convex. How can you convince yourself it's non-convex? Well, in a couple ways. One is just plot it. You can see how it's non-convex. And I wanted to minimize this subject to the constraint that x was bigger than or equal to this value minus 4.5. Right, so the minimum value is obvious once we plot it. It's just given by this red line. So this is not an interesting problem from the perspective of solving it being difficult, but it's interesting in that when you look at the dual function being concave, it tells you something interesting. So you can actually derive the dual function explicitly here. Why can you do that? It's because when I add this constraint, I'm going to be adding something that looks like minus u times x, or u times the quantity x plus 4.5. Right? So if I add this constraint, if I form the Lagrangian, L of xu is x to the fourth minus 50x squared plus 100x. Then it's going to be minus ux minus 4.5u. Right? That just comes from adding u times minus x minus 4.5. And now to form the Lagrange dual function, I have to minimize this over all x. But so these are, to minimize this, that's finding the root of a cubic equation, right? Because I have to take its derivative and set it equal to 0, and then look at which root basically gives me the minimum. And there are closed form expressions for that. It's very messy, but there are closed form expressions for that. So I was able to write down a closed form for G here, even though it was a non-convex problem. And I got this form of G that was very complicated. It had powers of u in the numerator and the denominator, and had fractional powers of u. It was a very complicated expression. And if I looked at it, there was no way I could tell whether it was concave or not. It was too complicated. It didn't look like it came from operations over simple functions. It was just a complicated expression. But I knew ahead of time that it is concave. That's what's interesting about it. This very complicated function I knew had to be concave because I knew it was the dual function of some problem. And when I plotted it, sure enough, it is concave. It looks piecewise linear, but if you look carefully, there's actually a lot of curvature just at a kind of a small scale. Okay, and here we see another example of where we look at the dual function. It's a function of one variable. Here I called it u on the notepad. Its maximum, look, it never reaches the minimum value of the primal criterion. So here we see, again, we don't get equality of the two criterion values. So that brings us to our next point, which is strong duality. So we're interested in figuring out when we have this relationship between the primal and the dual problems. And I posed the question last time, when do people think that's the case? And somebody guessed for convex problems, and that's basically the right answer. Basically, it's the case that for convex optimization problems, we get strong duality. There's just a very kind of minor detail that we need to pay attention to, which is that if we have a convex problem, so that means that when I write down this problem, right, minimize f of x subject to hi less than or equal to 0 and lj equal to 0, that f has to be convex. the H's have to be convex, and the L's have to be affine. So if this is true, and there is an X such that I can meet all of these, I can meet all of these equalities and all of these inequalities strictly. Then I get strong duality. Okay, so for most problems you write down, there is going to be a point that lives in basically the relative interior of this constraint set. That's all this is saying. I can find an X that makes it so that Hj of X is less than 0 strictly. So these two conditions together are sometimes called Slater's condition. The problem is convex, and we can meet the inequality constraints strictly and the equality constraints, then we get strong duality. So it's a pretty weak condition already. It can be even further refined, which is that I can actually make it so that I only need to satisfy hi of x less than 0 for all I such that hi is non-affine. So if I actually have affine inequality constraints, I don't even need to check that I can satisfy those strictly. I can just look at the ones for which hi is non-affine. So this is like an even weaker form of Slater's condition. Okay, so you look at a problem, you check that it's convex, and you check that you have either this kind of feasibility requirement or this even weaker one, then you know that you have strong duality. So you know if you could derive the dual function in closed form, and you could maximize it, then you get the same value as if you minimized your original problem. So we started this lecture off on Tuesday where we talked about LPs. And we asked the question, when do we get strong duality in LPs? Right? We had the max flow min cut problems that were dual. We derived a bunch of duals by hand for smaller problems. And so now we're going to answer the question for LPs in particular. So for LPs, remember I have that all of the HIs themselves are affine. So all I need to happen for strong duality in LPs, I get strong duality if the problem is feasible. Right, so in other words, all I have to do is find some x such that this is true for all I and for all j. And as long as I can find that x, then I get strong duality in LPs. That comes from this weaker version of Slater's condition. So what does that mean for us? That means the following. If you take the dual of an LP, and then you take the dual of that, you can go through this exercise on your own after lecture. You can check that you actually get the original LP back. You don't get like a third problem. You get the same original problem. So in other words, the dual of the dual LP is the primal, the symmetric relationship with LPs. So when I apply Slater's condition, I know that strong duality holds for this original LP if it's feasible. So if my LP is feasible, then I get strong duality, which means that F star equals G star. Let's apply the same logic to the dual LP now. So I'll call the dual LP DLP. If the dual LP is feasible, then again we know that strong duality holds. For it, and its dual. But its dual was the same problem as the original one. Right? So I'm just concluding that G star is equal to the optimal value of its dual criterion. But its dual, like we said, is just the primal. So I know that G star is equal to F star. So the only way I can get I can not have strong duality in LPs are when both the primal and the dual problems are infeasible. That's pretty rare. So it exists, and I think, I'm not sure because I don't remember, but I think on your third homework, you have a problem in the mastery set where you look at feasibility. I'm not sure if one of the problems is a problem in which this is the case, but there are problems, there are LPs in which both the dual and the primal are infeasible, but they're very peculiar. You don't really encounter them very often. So in other words, you can think the takeaway message that you always get, pretty much always get strong duality for LPs. Okay? And if you're worried that you're not going to get strong duality, look at the dual, look at the primal. If either one is feasible, you'll have strong duality. So I'm not going to cover this mixed strategies for matrix games. It's interesting. It just has to do with LP and duality. It has an interesting implication kind of from a game theoretic perspective. And it has a historical interest also because duality was first explored in the context of LPs, and this was one of the questions that people are most interested in answering. So I think Yifei is doing the recitation this week. Maybe he can cover this in the recitation. OK, let's take a quick break, and then we'll come back to the Kkt conditions. Most, or tied with the most useful thing that you can take away from this course. I think that we learn lots of interesting things, but this is one of the things that you'll see either by far the most often or tied for the most often as you do optimization beyond this course. It plays a role in almost everything. So out of curiosity, how many people have learned these Kkt conditions in another course or have seen them before? OK, so we have a good fraction of students who've seen some form of the Kkt conditions. Today we're going to actually we're going to build them from the ground up using duality. So we're going to prove through a bunch of very simple arguments the sufficiency and the necessity of the Kkt conditions for optimization problems. So again, it's one of these things where the arguments are like a couple lines long, but you get something very powerful out of it, which is a bunch of conditions that are equivalent to optimality. So it comes from duality. That's why we learned duality first. You can think about it in other ways than duality, and I'll talk about that after we learn the Kkt conditions. All right, so I don't need to really go through this slide because we just came from this lecture. But we have a Lagrangian and Lagrange dual function that are associated with this optimization problem. And summary of all this stuff: dual problems always convex, dual functions always concave. We get weak duality always, and strong duality under Slater's condition. So if the problem's convex and we have a feasible point that satisfies the inequalities strictly. So a couple important things to point out before we talk about the Kkt conditions. One is the duality gap. So the duality gap is defined as the quantity f of x minus g of uv if I have a pair of primal feasible and dual feasible points. So if x is feasible for the primal, and I have u bigger than or equal to 0 and v, then this is called the duality gap between my primal and dual problems at these points, x and uv. So why is that a useful quantity to have a handle on or to know in practice, say? It's because of this relationship. If we look at f of x and we subtract off the optimal value of the primal criterion f star, then I know that, for example, f star is lower bounded by GUV. That just comes from our duality construction. Any dual feasible point provides us with a lower bound on the primal optimal criterion value. So what does that mean? That means that f of x minus f star is at most f of x minus GUV. So this is actually very useful, because it tells us that how far we are away from optimum in terms of our criterion value is no more than the observed duality gap. This is something that we can actually observe in practice. Suppose we ran an algorithm where we were trying to simultaneously minimize the primal problem and maximize the dual problem. So we had a guess at x for our primal solution, and we had a guess at uv for our dual solution. If we just plug in f of x minus guv, then we know that how far we are away from optimal, and from the optimum in the primal criterion is no more than that gap. So if we want to be, say, within, epsilon of the optimal criterion value, then we could just make sure the duality gap is smaller than or equal to epsilon, and we know that we've done our job. With f of x minus f star is less than or equal to epsilon. So this is a very useful quantity, especially in iterative methods that try to solve the primal and the dual problem simultaneously, because we can, at every iteration, just check the duality gap. So this is a very rigorous way of stopping. It's a more rigorous way of stopping iterative algorithms than what we've learned so far, which is we haven't really given you a very rigorous way of doing that. And on the homeworks, you've done stuff like look at the change in the criterion value from one iteration to the next, or the normalized change, or something to do with the iterates themselves, how much they change. And those are kind of heuristic ways of stopping an iterative algorithm. But this is a much more rigorous way of stopping. Okay, and something trivial to point out that will be useful for the Kkt conditions, if I have the duality gap being 0, then what does that imply? That implies actually that x is primal optimal and uv are dual optimal. Why is x primal optimal? Well, if this is 0, since this is always bigger than or equal to 0, this also must be 0. So I have that f of x equals f star, so x is primal optimal. That's definitely true if the duality gap is 0. Why are u and v dual optimal? Well, I can get the analogous relationship in terms of g. I get the guv minus g star is bounded by the duality gap also. Right? So if it's 0, I also get that u and v are dual optimal. So as long as the duality gap is 0, we have the solution to both the primal and the dual problems. Okay, dual norms. I'm going to skip this because we're going to talk about it in detail next time. But this was just a preview of it. I stuck it in case we had time, but we'll cover dual norms in detail at the next lecture. So here's what we'll talk about: Kkt conditions, examples, and then that'll probably be it for this class, but we'll continue on Thursday, and we'll talk about a few more things after that. So the Kkt conditions, I'm just going to go ahead and state them. If you have this problem, it's our canonical form for an optimization problem. Again, we're not assuming convexity at this point. We're just writing down an optimization problem. Then the Kkt conditions, they stand for the Karush-Kuhn-Tucker conditions, are a set of 4 conditions that are the following. The first is often called the stationarity condition. It's that if I take a subgradient of the Lagrangian, remember the Lagrangian was L of x uv, it's f of x plus the sum of ui hi plus the sum of vj lj. This first condition, stationarity, it says that if I take a subgradient of the Lagrangian with respect to x, then that must contain 0. So 0 is in the subgradient with respect to x of L of x uv. So what is this telling us in terms of the role that x is playing for the Lagrangian? It's another way of stating the stationarity condition. What does it mean for a function to have a 0 subgradient at a point x? What's that? It's the minimum, yeah. So it means that L of x uv is the minimum, say, over all x tilde of L of x tilde uv. This means that the point we have x minimizes the Lagrangian over all other candidates. That's the stationarity condition. The next one is called complementary slackness. It just says that ui times hi of x is equal to 0 for all I. So remember that ui was always bigger than or equal to 0, and hi of x is always less than or equal to 0. So this is telling us that with respect to those two constraints, one of them has to be tight. I can't have both that ui is strictly negative and hi is strictly positive. I must be having either ui is equal to 0 or hi of x is equal to 0 or both. And the last two conditions are very straightforward. They're just primal and dual feasibility. So I have to have x satisfying my constraints, and I have to have u and v satisfying the dual constraints. That's just being that ui is bigger than or equal to 0 for all I. So these four conditions, in a sense that we're going to make very precise, they completely characterize optimality. So for very general problems, x is primal optimal and uv are dual optimal if and only if these four conditions hold. Okay, and we're going to prove both directions right now. So before we do that, are there any questions about these conditions? Okay, so let's go the one direction, necessity. So that means that we're going to show that if I have x star and u star, v star being primal and dual solutions respectively, then we must have the Kkt conditions holding. Okay, so this is the one direction necessity. So let's assume these are optimal. And let's assume one more thing. So assume that these are optimal and that strong duality holds. Okay, so in that case, I have that I have f of x star is equal to g of u star v star. Right? That just comes from strong duality. Directly, that was our assumption. And what was this? Remember, by definition, the dual function at u star v star is the minimum over all x of the Lagrangian. So f of x plus ui star hi of x plus vj star lj of x. And the minimum over all x is in particular less than or equal to the Lagrangian evaluated at x star. Right? I have to get less than or equal to when I plug in x star here. And now because, this should be an x star, because I have that x star was a solution, it's optimal, we know it has to be feasible. So that means that this has to be less than or equal to 0, and this has to be equal to 0. I know that because u was a dual solution, it also has to be feasible, so this has to be bigger than or equal to 0. Right, so this whole thing can be no more than f of x star because this term here is 0 and this term here is negative. Okay, so all I've shown in really just two lines, because these are equalities, these are the really substantive arguments, is that I have f of x star, right, less than or equal to f of x star. Well, because of these kind of two trivial upper and lower bounds, I know I get all equalities here. I conclude that actually here I get an equal sign, and here I get an equal sign also. So all the inequalities are actually equalities. And now we're going to just read off of a few of these, and we're going to get the Kkt conditions from the fact that these are equalities. So the first thing I get is that the minimum over all x of the Lagrangian is equal to what happens when I plug in x star. So that just means that x star minimizes L of x u star v star. That's the same thing as stationarity. Right? So I conclude the stationarity condition must hold. Okay, so that part's met. How about this next line? Well, let's look at now the fact that this is equal to this. Well, this is 0, and for this to be equal to this, all of these terms here in the sum, they're all actually less than or equal to 0. Like I said, the product is something that's bigger than or equal to 0 times something that's less than or equal to 0. So the whole thing is less than or equal to 0. And for this to be equal to f of x star, I need to have that this entire term is 0, because all the individual terms in that sum are of the same sign. Every individual term has to be 0 also. Right? So then I also conclude that I get ui star times hi of x star is equal to 0 for all I. In other words, that's what we call complementary slackness. And of course, the last two conditions we know must be true. We know that x star and u v star have to be primal and dual feasible because they were solutions. So they have to be true. And then those four things are the Kkt conditions. So we've just shown that if x and uv are optimal points and strong duality holds, then the Kkt conditions must also hold. Okay, so again, I'm going to point out that there's nothing here that we assumed about convexity. We just assumed that strong duality held. So if we happen to have a problem in which strong duality held, and we had x star and uv star, then we know the Kkt conditions must also hold. Okay. How about the other direction? The other direction is the direction in which we know the Kkt conditions hold, and we want to figure out whether or not the points that satisfy those Kkt conditions are optimal. So that's the sufficiency. So we have that x star and u star v star satisfy the Kkt conditions. Right, so it's slightly an abuse of notation to write the stars here because we don't know that they're optimal yet. They're just points that satisfy the Kkt conditions, but we're going to prove they're optimal in a second. So if they satisfy the Kkt conditions, then I know that g of u star v star is equal to, well, I know it's equal to, first of all, the minimum over all x of L of x u star v star by definition. And now I'm going to invoke stationarity, the stationarity condition, and write this as f of x star plus the sum of ui star hi of x star plus the sum of vi star or vj star Lj of x star. That was just stationarity, right? The fact that x minimized the Lagrangian, or that x star rather minimized the Lagrangian, allows us to write that. And now I'm going to use complementary slackness and call this term 0 by complementary slackness. I'm going to use the fact that x star was primal feasible and call this term 0, because Lj of x star is 0. And I get that this is just equal to f of x star. So what have I concluded? I've concluded that the duality gap is 0. At x star u star v star. But that means we know from just a few minutes ago that they're optimal. Right, so we just proved this direction. Okay, so again, there's nothing here about convexity. We know that if I have any points that satisfy the Kkt conditions, then they must be optimal. So let's summarize what we've seen. They're always sufficient. So as long as you satisfy the Kkt conditions, you have optimal solutions. And they're necessary under strong duality. So as long as strong duality holds, if I have optimal points, I must also have the Kkt conditions being satisfied by those points. So putting it together, this is usually the way you hear it stated. If I have a problem where I know strong duality holds, then the Kkt conditions are necessary and sufficient. They're equivalent to optimality. And what are the problems in which we know that strong duality holds? Well, right, the most general set of problems are those that satisfy Slater's condition. So they're convex, and there's an x that strictly satisfies the inequality constraints. Okay, so that's the summary of what we just showed in a few lines there. Are there any questions about this? The algebra, like I said, is very simple, but this statement is very non-trivial. And it's a very, very useful fact to know. Okay, so one thing I wanted to point out as a warning is that, this is true. The Kkt conditions are always sufficient. So for a non-convex problem, if I have x and uv satisfying the Kkt conditions, I do have an optimal primal x and an optimal dual u and v. But there's one kind of thing to pay attention to, which is that if I have a non-convex problem, then the stationarity condition may not be what you think it's saying, even if the problem is differentiable. So the stationarity condition, what happens if f and h and L are differentiable? If all those functions are differentiable, what does it look like? What do you guys think it looks like? It's 0. If they're differentiable, then there's only one subgradient, right? So it's 0 equals the gradient of f of x plus the sum of ui times the gradient of hi of x plus the sum of vj times the gradient of lj of x equals 0. So that's maybe how you see it, how you've seen in other classes. That's the more typical way of writing it. So is this stationarity? Is this the same thing as stationarity condition? I see some nodding yes. Does anybody think it's not? No, it's not the same. Because right, so this is the same thing as stationarity, as long as f, hi, and Lj are convex. For convex functions, their subgradients are their gradients if they're differentiable. Right? For a convex function, if it's differentiable, its subgradient is its gradient. But for a non-convex function, they're not necessarily the same thing. Remember, we have the examples like this, for example. This is a smooth, non-convex function, but its gradient at this point is not a subgradient. In fact, it does not have a subgradient at that point. Right? So it's important to remember that if you have a non-convex optimization problem, even if it's smooth, it is true that the Kkt conditions are sufficient. If you manage to find xuv that satisfy them, you have the solution. But this is not the same thing as satisfying that stationarity condition. So you can't just write down the stationary condition in terms of gradients and satisfy it and think that you have a solution. You have to make sure that it's subgradients. So that's why I've written it as subgradients here. And just be careful, depending on where you read, this distinction may not be incredibly apparent. So if you actually read the Boyd and Vandenberg book, they write it in terms of gradients. They don't introduce subgradients in that book. And they kind of subtly in various places say they need convexity for certain things. But if you read it quickly, you might forget that this is really intending to mean subgradients. Okay, so it's kind of interesting, the story of the Kkt conditions. I'm not old enough to have claimed that I ever learned them when they were called the Kkt conditions, but and I don't think Barnabas would have learned them as the Kт conditions either. But for a long time, they were just called the Kт conditions. So if you read that Rockefeller book that we put as one of the optional references, that was written in 1970, I think, and at that point, they were called the Kт conditions, not the Kkt conditions. And the history was that Kuhn and Tucker are these two optimization kind of giants. They're both very famous. They published a paper in 1951 that contained these conditions. So people attributed these conditions to them, and they're called the Kт conditions all the way up until, I believe, I don't know exactly when, but I believe well past the 1970s. But then later, people found out this individual, Karouche, he actually had these conditions in his master's thesis. So that was a pretty good master's thesis. And it was unpublished, too. And it was way earlier. It was 1939. So then we appended the K to the front to call them the Kkt conditions, where the first K is for Karouche. So if you read old textbooks or old papers, they might still call them just the Kt conditions. Another notational thing or a lingo thing is that a lot of people use the term Kkt conditions to refer to just that first thing, the stationarity condition. Because if I have an unconstrained problem, there's no constraints, then the Kkt conditions are just this. Right? In the absence of constraints, it's just the same as stationarity. So a lot of times you'll hear people talking about the Kkt conditions for unconstrained problems and writing down this, and that's all it reduces to.
If there are no constraints, don't you only just get zeros in the subgradient of f?
Yeah, so that's just the subgradient condition. Yeah, that's a good point. But so sometimes, I mean, we'll see examples of problems where they don't have constraints. And in order to derive the dual, we add constraints. But the original primal problem is unconstrained. So it still makes sense to talk about a dual problem. That'll be the case for the lasso, actually, when we derive its dual. So even though the original problem doesn't have constraints, we can derive a dual by adding constraints. And then the Kkt conditions, when we talk about them in one form, they'll just refer to the subgradient optimality. That's it. So another thing to point out is that we derive these from the perspective of duality because that was the simplest way to do it. We had one lecture on duality where we learned the ins and outs of duality. Again, very simple arguments, but very powerful results. And then we proved the Kkt conditions in a couple of slides. Alternatively, you could have gone through the entire thing via subgradients. So if I had this problem, this constraint optimization problem, I know that x star is an optimal point if and only if it's a subgradient of the criterion. Or sorry, if and only if 0 is a subgradient of the criterion at x star. And I could have written the constraints as indicators, right? I could have written the problem as f of x plus the sum of the indicator that hi of x is less than or equal to 0 plus the sum of the indicators that Lj of x is equal to 0. And I could have said that x star minimizes this if and only if I have that 0 is a subgradient of this whole thing at x star. Well, what are the subgradients of this? They're the subgradients of f plus the sum of the normal cone of this constraint set, right? At x star plus the sum of the normal cone of this constraint set at x star. Right, because the subgradients of the indicator functions we know are just the normal cone. So in other words, 0 is in this if and only if x star is optimal. And you could have gotten the Kkt conditions from just exploiting this relationship. But it's much more complicated in terms of the calculus required. It gets quite difficult. But they come from this also. And this is how Rockefeller derives them in the book that we recommended as an optional reference. So you can take a look if you're interested to see why they come from this and how they're constructed. But make sure you have a lot of energy because it's very, very dense reading those few chapters. It's not easy to read. So in the time we have left, I just want to go through a few examples of the Kkt conditions and what they do for us. And then that's going to be really the next lecture is going to be what do the Kkt conditions and duality do for us in general. It's a very beautiful relationship, but it's actually also very practical. And that's what we'll talk about on Thursday. And so then we're going to kind of ramp up to that now. So the first is a very simple example. Let's suppose we have a quadratic with equality constraints. So I want to minimize 1/2 x transpose qx plus c transpose x subject to ax equals 0. Okay, so if I didn't have this, if I didn't have that, I feel like I've asked this question a few times in class and I have not gotten an overwhelming response. What's the minimizer of this problem? X star is what? Is that the right sign? Minus, right. Okay, so we have a closed form for the solution for the unconstrained problem. How about the equality constrained problem? The Kkt conditions can give us a way to find that also. Okay, why would you be interested in this problem? Well, maybe it comes up in some context out of some, some scientific problem. But in terms of optimization, it also comes from doing equality constrained Newton's algorithm. So if I have this problem, minimize f of x subject to ax equals b, and I do Newton's method for this, then every iteration of Newton's method, I'm solving a problem like this. Because I want to move in the direction basically minus, if I didn't have this equality constraint, I'd move in the direction minus the Hessian inverse the gradient. That would be my Newton step, right? I'd take x plus is equal to x minus the Hessian inverse the gradient. But in the presence of this equality constraint, I can't just take this because I might leave this constraint set. So what I want to do is I want to move in the direction that minimizes the quadratic, where this q is now the Hessian, subject to taking a step in that direction, not changing ax. Right? So if I had that, suppose I had x satisfied ax equals b, then I want to write x plus equals x plus delta, where delta satisfies a delta equals 0. So once I take this step, I'm also having ax plus star equals b. And also, I need delta to minimize 1/2 the Hessian times delta transpose the Hessian delta plus the gradient transpose delta. And I want delta to minimize this. This is like my quadratic approximation around x. So I do equality constrained Newton's method. It reduces to solving minimize this subject to a delta equals 0, or just this problem we wrote down right here. So this is kind of as an aside. So Newton's method. Okay, so back to this. How do we solve this problem? Well, let's write down the Kkt conditions and see what they tell us. There's no equality constraints, or no inequality constraints. And we have the equality constraint ax equals 0. So let's write them down in order. Stationarity tells us that if I have the Lagrangian L of x, say v, which is going to be 1/2, or I guess I called it u here, but it's not that important. X transpose qx plus c transpose x plus, what do I add here to form the Lagrangian? Right, so another way of writing ui times each of those equality constraints and sum them up is just u transpose ax. And so the stationarity condition says that x has to minimize this. In other words, I have to have, because this is convex, I can just say that 0 being a subgradient, it's saying like the gradient is 0 at x. So that means that qx plus c plus a transpose u equals 0. That's stationarity. How about the next one was complementary slackness? Well, there's nothing, right? Because there's no inequality constraints. And the next one was primal feasibility. So that just tells us that I have to have ax equals 0. And the last one was dual feasibility. Well, again, because I have no inequality constraints, there's nothing here. Because with equality constraints, I have no constraints on that dual variable. So the Kkt conditions reduce to just these two conditions here. And we know, because this is a convex problem, and I have that all of the inequality constraints can be satisfied strictly. There are no inequality constraints, so certainly that's true. That the Kkt conditions are equivalent to optimality. So they're the same as finding an optimal point. So in other words, x minimizes this problem if and only if I have these two things. And I can write these in a more concise form. I'll just write q a transpose a 0 x u equals minus c 0. All right, so the first block of this system of equalities gives me qx plus a transpose u equals minus c. That was stationarity condition. And the second block gives me ax equals 0. That was just primal feasibility. So again, there's actually an explicit solution here, right? We just invert this matrix. The first block gives us the primal solution. The second block gives us the dual solution. Okay, here's a problem that's a nice problem taken from your textbook. Take a look at this problem. It looks like it is a fairly challenging problem, right? I have an equality constraint on x, my variable, summing up equal to 1. I have x being non-negative in every component, and my objective function is a minus sum of logs. Right? So it's not obvious that this is easily solved. But it turns out that when we take the Kkt conditions, we'll reduce this to a very simple system of qualities that have to be solved that we can solve almost analytically. Not quite, but with a very simple algorithm. So that we can find x basically directly from the Kkt conditions. The motivation that the authors of this book give for this problem is an information theory one. So they say that think about x as being a vector of weights. So I want to figure out how much of my resources to allocate to maybe n different sources. So each component of x tells me how much to allocate, what proportion of my resources to allocate. And log of alpha I plus xi, alpha here is a constant that's given to us. This is like the communication rate of the ith channel. So I can also write this as maximizing the sum of log of alpha I plus xi subject to x bigger than or equal to 0 and 1 transpose x equals 1. This is saying like I want to maximize my communication rate by allocating my resources appropriately. Okay. So what are the Kkt conditions for this problem? We'll think about it in its original form. Minimize minus the sum of log alpha I plus xi. So let's go through them one at a time again. Stationarity says that I have to have 0 being a subgradient of the Lagrangian at x. So first, the Lagrangian, I have both x and u and v here because I have equality and inequality constraints. It's minus the sum log alpha I plus xi, and then I get minus the sum of ui xi. Right, because I can write this as minus x being less than or equal to 0. And then I get plus v times 1 transpose x minus 1. That's the Lagrangian. And we want to say that for the stationarity condition that x minimizes this over all x. So again, this is a convex function of x, so it's the same thing as saying that the gradient of this at x is 0. So what's the derivative, say, with respect to xi of this Lagrangian? So I have that, I take the derivative of this first term with respect to xi. I just get minus 1 over alpha I plus xi. Make this slightly bigger in case it's hard to see. The sum of the log of alpha I plus xi. And now this term contributes a minus ui, and this contributes a plus v, right? So I can write that as this as the sum of xi minus 1. So the stationarity condition says this has to be equal to 0 for all I. V is a scalar, that's right. What's that?
In your Lagrangian, you wrote vi.
Oh, thank you. Yeah, that we just have one v because we have just one equality constraint. So now complementary slackness tells us that ui times xi has to be equal to 0 for all I. That's our inequality constraint right there, xi being less than or equal to 0. And then primal and dual feasibility. Primal feasibility is just that these guys are met, the original constraints. And dual feasibility tells us that u has to be bigger than or equal to 0. So these characterize optimality again because the original problem was convex, and there is a point obviously that satisfies the sum of x being equal to 1 and x being strictly positive in every component. So then we get that the Kkt conditions are equivalent to optimality. So we're just going to work through these, a few simple manipulations. When we look at this, one thing to realize is that we can actually eliminate u from this system here, from these 4 conditions. So the first thing I'm going to do is I'm going to rewrite complementary slackness as ui times, I'll solve for xi times ui equal to 0, I'll solve for ui in this system. And that just gives me v minus 1 over alpha I plus xi equals 0. So that's complementary slackness after I've eliminated ui. Okay, I'm going to now combine dual feasibility and the stationarity condition to get rid of ui. I'll rewrite those as my new stationarity condition combined with dual feasibility, which is that v minus one over alpha I plus xi. So originally I would have had this equal to ui. That would have been from the stationarity condition. But I know that ui has to be bigger than or equal to 0. So I can just write that this is bigger than or equal to 0. All right, it's equal to some value bigger than or equal to 0. It's equivalent to this being true after I substitute in for ui here. So there's no loss of generality here. As long as x and alpha satisfy these three things, I still have to have the primal feasibility. Then there is an xVu triplet that satisfies my original Kkt conditions. Questions about that? All right, so from this now, make another observation. So we want to solve these for x, I, and v. Want to do that, we have the solution in x to our problem. So we take a look at it, and we think about two cases. The first case is if, let's suppose that v was smaller than 1 over alpha I. Okay, so if v is smaller than 1 over alpha I, then since xi yeah, so if v is smaller than 1 over alpha I cannot have xi being equal to 0. Because if that were true, then the first component would tell me that v is bigger than or equal to 1 over alpha I, my stationarity condition, right? So I must have that xi is strictly bigger than 0. And now in order to make complementary slackness met, if xi is strictly bigger than 0, then this whole term has to be equal to 0. So that means we have to have v equals 1 over alpha I plus xi, or in other words, we have to have xi equals 1 over v minus alpha I. And if v was bigger than or equal to 1 over alpha I, then now I can't have xi being bigger than 0, because if xi was bigger than 0, then this thing, their product is not going to be 0. Because if v is bigger than or equal to 1 over alpha I, and xi is positive, it's strictly bigger than 1 over alpha I plus xi, so I have a positive times a positive. So I can't have it being strictly positive, and I must have it just being equal to 0. So in other words, we have an explicit solution for x as long as v is kind of on one or the other side of this boundary. So we can write that xi, to summarize, xi is equal to the maximum of 0 or 1 over v minus alpha I. So that's our solution for xi in terms of v. And now we plug that into our Kkt conditions. And in order for for x to be feasible, look, this is always bigger than or equal to 0, because it's at least going to be 0. Right? We still need the fact that we get the sum of the x's being equal to 1. So we need 1 is equal to the sum of the x's, which after we've substituted in for v, that's equal to the maximum of 0 and v minus 1 over alpha I. I think I have this backwards here. 1 over alpha I, no, 1 over v. Yeah. So we reduced all of our Kkt conditions to just a single system, one linear equality in one variable v. V is just a single variable, right? So as soon as we solve this for v, it's a univariate optimization problem, we get x from this relationship, and then that solves our problem. So through the Kkt conditions, we've reduced solving this optimization problem, which looks very hard, to solving this equality, this one kind of system of equalities in one variable, just in v. And we can do that in multiple ways. But since v is univariate, you should convince yourself this isn't hard to do in any case. Because I can kind of take a guess at v and then just move it around depending on whether or not that guess is wrong. Okay, there are more clever ways to do it than that. The reason why it's called the water filling problem is because there's a way to solve this with the analogy to filling a structure like this with water and stopping at the right point. But regardless of how clever that is, you could just fool around with a very simple univariate algorithm to get a solution to that, right? Because v is just a single variable. Okay, so that was our example of how a hard problem reduced to an easy problem from the Kkt conditions. We're going to see lots more examples like that on Thursday, also when we bring back duality into the mix. See you then.